All right, welcome to this section of which is the first section of this next unit, which is going to be titled Riemann Sums. And that is the correct pronunciation, as far as I know, for this is Riemann. Calculus 1 can be broken up into two major classifications. You're going to have differential calculus, which is going to be your first half of your calculus dealing with derivatives. And then the second half of calculus is going to be what is called integral calculus. This is going to involve the use of integrals to study the area underneath a curve. So this section marks the beginning of the study of integral calculus. And in order to talk about integrals, we must first determine what it is we are trying to find. Once we figure out what we're trying to find, then we decide how we are going to find it. This will have further implications, which will lead to many types of applications that involve the use of derivatives and integrals interacting together to evaluate the motion of the world around us. So what is it we're trying to find? The answer to that is going to be the area between the curve and the x-axis. And this will be between any curve and the x-axis. That area can represent a lot of different things. And so how are we going to find that area? Well, we're going to build up to that, looking through some examples here. All right, so suppose you need to find the area under the curve y equals 1/2 x, which is given right here as this line segment between x equals 0 and x equals 6. You should first start with a sketch to give you a visual of what you're trying to find. And so as you can see, the area is going to be fairly easy to find because it's simply the area of a right triangle. And so if I was going to find the area of this, I would just simply multiply my base, which is 6, times my height, which is 3, and divide by 2. And that would give us an area of 9. Sometimes the shape formed between the curve and the x-axis is a recognizable shape from geometry, such as that triangle was. Many of these shapes have area formulas that you're familiar with, and so here are some examples here. And so what we're trying to do is find these areas right here. And starting out with the first one, this shape is your trapezoid. And trapezoid formula, base 1 plus base 2 times the height divided by 2, where your bases are the two sides that are parallel to each other. So that would be 3 plus 7. The height is the distance between your two bases, which is 4, divided by 2. It's going to give us an area of 20. This one is going to represent a circle. I know it doesn't look like a circle, that's just kind of the scale that was used on creating the graph. But this is a circle. It's actually a semicircle with a radius of 3, and your area of circle is pi r squared. So for a semicircle, we're going to divide that area by 2. So it's going to give us pi times 3 squared divided by 2, which is 9 pi over 2. Just leave pi in your answer on this. So your next one is going to have several sections. You've got this section, which is just a rectangle, which is base times height, plus the next section, which is a trapezoid. So that's going to be base 1 plus base 2 times the height divided by 2. All right. And then we have this triangle over here, which will be plus base, which is 4, times your height, which is 2, divided by 2. All right, so that's going to give us 10 plus, let's see, 21 over 2 plus 4. So that's 14 plus 21 over 2, which would be 28 over 2 plus 21 over 2, which is 49 over 2 for that total area. So sometimes you can break these off into sections and find the area of each section and then find the total area on this. Sometimes the shape formed between the curve and the x-axis is not a recognizable shape from geometry. In these situations, you will need to find the area by using other methods besides using a formula. And so you may not even be able to find the exact area in those situations. You may need to settle for finding an approximation of the area to the shape. So here's an example here. This is the function y equals 4x minus x squared, and our task is going to be finding the area in here, and so that would be all of this area in here. All right. So in order to approximate the area between this curve and the x-axis, you can fill up this area with shapes from geometry that you know the areas for. So we don't have a formula that involves parabolas from geometry. And if we want to find this area that has a curved surface to it, we can't really do that with a formula, but we can fill up this shape with all kinds of different geometry shapes that we do know the area formulas for. And that would give us a pretty good approximation for the area of this. The easiest shape to use is simply a rectangle because it has an easy formula for it. It's base times height divided by 2. So that's what we're going to use here. Because the upper limit is curved, using rectangles will not give us an exact area. The number of rectangles we use and the placement of those rectangles will also play into our strategy. So here what we're going to try to do is use 4 rectangles to approximate the area. And there are 3 different placements of those rectangles that we will use in calculus to approximate the area under a curve. And so one of them is going to be called middle rectangular approximation method. The other one will be left rectangular approximation method, or LRAM, and then a right rectangular approximation method, or RRAM. Now, one of the things you can think of is, well, if I try dividing this shape up, I can do that several different ways. If I just use one rectangle and try to say, okay, well, how close is that rectangle to being the approximate area under the curve? It'll give you an approximation. It will not be particularly accurate. And so what we want to do is try to get as close of an approximation as possible. All right, so we're going to start off with the MRAM method. All right, so the first thing we're going to do is divide up this area into 4 rectangles. And so we're finding the area between 0 and 4. So that means at 1, what we will do is come straight up. At 2, come straight up. At 3, come straight up. And then at 4, you would come straight up until you get to the curve, but the curve hits there. So what this does is it divides this shape into 4 rectangles. One here, one here, one here, and one here. Now with an MRAM, the way you do this is you look at this first rectangular section, and this represents the base of that rectangle. You're going to find the midpoint here, and you're going to come straight up until you hit the function. Where you hit the function, that determines where the top of your rectangle is going to be located. All right, so that means we're going to come straight up here. This becomes the top of our rectangle. The next rectangle, we find the middle between there, come straight up until it hits the function. That determines the top of our rectangle, which we can then finish off here. And then we do the same thing with this one, come straight up until it hits the function. That determines the top of your rectangle, finish it off. And then this one coming straight up gives you the top of the last rectangle, and then finishing it off. All right, so what we do then is we simply calculate the area of each rectangle and find the total area. And so the base of the rectangle is 1 on each one of these. So we have 1, 1, 1, and 1 for the bases. The heights are determined by the function. The function was 4x minus x squared. And so if you plug 1 into x, that's where, I'm sorry, not 1, 1/2. If you plug 1/2 into x, because that's how we get the height, is right here, that's going to yield this height. If you plug 1.5 or 3/2 in for x in the function 4x minus x squared, that's going to yield this height. And then 2.5, which is 5/2, plug it into 4x minus x squared, gives you this. And then our last one gives you this, for a total area of 11. Now, the next one is going to be what is called an LRAM. So we start out the same way, which is dividing up this shape into the 4 rectangular sections. All right, so we've got one section here, 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 and here. Now for an LRAM, we will come from the left side of each rectangle. Where the left side of the rectangle hits the function, that determines the height of that particular rectangle. Now for this rectangle right here, the left side is this side. This side hits the function right here at the origin. That means the height of this rectangle is actually 0. That's why we see 1 times 0. The base is 1, the height is 0. This is your next rectangle. For your second rectangle, the height here is determined by where the left side of that rectangle hits the function. And so that is determined right here. And the next, let's see, well, the base is still 1. The height is determined by an x value of 1. So that means if you take the function 4x minus x squared, which is our function, and we evaluate this at 1, you're going to get 4 minus 1, which is 3. That's where this 3 is coming from, evaluating the function when x is 1. So the next rectangle, if you follow the left side of that rectangle up until you hit the function, that's where you would draw the top of your rectangle and then complete the rectangle coming down. And we do the same thing for the last rectangle. And then when you calculate all of these values here, comes up to an area of 10. And then the last, or the next one is going to be called an RRAM. This is going to be a right rectangular method. Now we start out the same way, which is dividing our rectangle up into 4 equal sections, coming straight up till you hit the function. But this time, the height of each rectangle is determined by the right side of your rectangle. So for this first rectangle with a base right here, the height would be determined where the right side of your rectangle hits the function. Well, that's right here. That means the height is going to be an actual height of 0. The one to the left of it, this is our height coming across from the right side. And then the next one from this height coming across, and then from the right side coming straight across. That is your RRAM, or right rectangular approximation method. And this gives us an area of 10. Remember, these are approximate areas between the curve and the x-axis. Because the rectangles extend outside of the area desired in some places and left off some of the area desired in others, the approximated areas are not particularly accurate, especially for the ones that we just did, because we only used 4 rectangles. Because these were some very large chunks, we need to think about the way that we can make this area approximation more accurate. We can make this approximation more accurate by increasing the number of rectangles. This will reduce the amount of area in these extra chunks. So you can see from the above that in graph A, an LRAM approximation was used using 10 rectangles. And this gives you an approximation of about 10.56. Remember, the approximations that we used before for LRAM and RRAM was 10. And so because we are using more rectangles in this one, it's giving us a more precise approximation. This is going to be more accurate than those 4 rectangles. Graph B even uses more rectangles, and you're going to get an even closer approximation of 10.64 because we have increased the number of rectangles here. The exact area under the curve is actually 10 2/3, which gives you a pretty good approximation. And if we divided this up to even twice as many or 3 times as many rectangles, you would get a pretty good approximation of the area between the curve and the x-axis. So you can start thinking about this in terms of a limit as the number of rectangles goes to infinity. So in this situation, we're going to approximate the area between the function y equals 1/2 x squared plus 1 and the x-axis between x equals 0 and x equals 4 using 4 rectangles of equal bases, doing an LRAM, RRAM, and MRAM. And we're going to draw the rectangles on the graph provided to show all of our calculations here. And so with this, doing an LRAM first, remember that we come up from the left, and what I did is I already divided this up into the 4 equal sections here, okay, coming straight up to the function. LRAM, we're coming up from the left side of the rectangle where it hits the function. That determines the height of our rectangle, so we come straight across from there. And that's going to give us this height right here. The next one comes from here going across, from the left side here across, and the left side here going across. All right, so that is going to give us the area of this, plus this area, plus this area, plus this area right here. Now the area of each of these rectangles is going to be determined by this function right up here, 1/2 x squared plus 1, evaluated at the different heights. I'm going to take a second here and go ahead and write all those out so that you can see that. All right, so what we have here is then going to be our calculations for, now each of these rectangles has a base of 1, and so you can see base times height, base times height, base times height, and base times height. The height of each rectangle is determined by the left side of the rectangle. So the first rectangle would be y of 0, which is this height, 1. The next rectangle would be y of, or the function evaluated at 1, and that ends up being 3/2. And so all these are your calculations for your heights at y of 0, y of 1, y of 2, and y of 3. And that gives you a total area of 11. Now you can see here that we have this chunk that is actually this one, this one, this one, and this one. If we think about these chunks in here, these are actually part of the area between the curve and the x-axis, and because those areas were left off of the actual calculation here, we can consider this to be an under approximation. Or an underestimate of the actual area between the curve and the x-axis. All right, so the next one we're going to do is a RRAM. So we're going to come from the right side, where the right side of the rectangle hits the function, and come straight across. The right side coming straight across, and then we complete out the rectangle. Come straight across, complete out the rectangle, and likewise here as well. All right, so now what we are doing is calculating these areas in here, and we've got this area, this area, this area, and this area over here. All right, so go ahead and take a second. I'm going to go ahead and calculate these areas and write them down. All right, so welcome back, and what we have now are the areas. These represent the heights once again. So we have 3/2, 3, 11/2, and 9. Notice that we're doing y of 1 as our first one instead of y of 0. And our last one is y of 4 instead of y of 3 for the height of the last rectangle. Now I calculated the area a little bit differently. Instead of writing 1 times this plus 1 times this plus 1 times this plus 1 times this, I just factored out that 1, which means we can just do that if the base value is the same all the way across. That allows us to just add up the heights and then multiply the height times the base value. This comes out to be 19. And we can see, because we have this chunk, and this down here that were calculated into this value, and yet this is not actual area that's underneath the curve and the x-axis. And so because of that, this is going to be an over approximation of the actual area between the curve and the x-axis. All right, so the last one we're going to be doing is going to be an MRAM. Remember, with the MRAM, you go straight up the middle. Where this hits the function, that's where you draw the height. Come straight up the middle. Where it hits the function, that determines the height of your rectangle. And do the same thing here. That's the height of your rectangle. And then the last one here comes straight up. That's the height of our rectangle. All right, so what we would do now is we would calculate the area between the the area of each of these rectangles and total those up. I'll go ahead and do that off the video here for a second. All right, so all these heights then are calculated at these sections here. This is the middle of the first rectangle, middle of the second rectangle, and so on, giving us these fraction values over here, and then adding up the heights and multiplying the base gives us this, which is 14.5 for the approximation for the area. Now this one is going to be a little bit more accurate because we have this section right here that's not included in the area calculation, but then we have this which kind of balances out those sections. So this becomes a little bit more accurate of an approximation. So look back at the LRAM approximation in that example that we did. Do you think your approximation is an underestimate or overestimate of the actual area between the curve and the x-axis? Is the RAM approximation an overestimate or an underestimate of the actual area, and why? So we can make some determinations based upon this problem here. If a function is strictly increasing, then a left approximation will always give you a underestimate or under approximation. If a function is strictly increasing, then a right approximation will always give you a overestimate or over approximation. If a function is strictly decreasing, then a left approximation will always give you a over estimate. And if a function is strictly, this should be decreasing. If a function is strictly decreasing, then a left approximation will always give you an underestimate. Let me correct something here. This should have been a right approximation will always give you an underestimate if your function is decreasing. All right, so rectangles, these are not the only shape that you can use with this process. Trapezoids are often used as well. So what we're going to do is use 4 trapezoids to approximate the area between this function and the x-axis between 0 and 4. So if you think about drawing your trapezoids, we start with the same thing, which is drawing the sides or the bases of the trapezoids until they hit the function up here at the top. And then all you're doing is connecting those tops. Now, what that does then is it gives you a really good approximation, and you would just simply calculate the area of this trapezoid plus this one plus this one plus this one. I'm going to leave that arithmetic up to you and not proceed with that part. So in this situation, this is going to give you are we going to have an overestimate or underestimate in this situation? When you're using trapezoids, you will know that it is an over or underestimate by looking at the concavity of the function. For example, if you have a graph that is concave up and you are doing these approximations, what's going to happen is you are going to have this chunk that is not underneath the curve. And so when you have a function's concave up, you are going to end up with an overestimate. If you have a graph that is concave down, and you do your trapezoids, you have this section here that's not being included, so that is going to give you an underestimate. So key thing to remember here, when you are doing trapezoidal approximations, being an overestimate or underestimate is determined by the concavity, whereas using rectangular method is determined by whether the function is increasing and decreasing, as well as doing a left versus a right Riemann. All right, so here is a situation given to us. The table below shows the velocity of a model train engine moving along a track for 10 seconds. Estimate the distance traveled by the engine using 10 sub-intervals of length 1. We're going to do this with an LRAM, RRAM, and with trapezoids. And remember that distance is equal to rate times time. When you find the area of the shapes, you're multiplying the rate times the time, which will give you the distance. So the approximated area actually represents the distance traveled by the train. All right, so do an LRAM approximation of this one. The first thing we did is plotted all the points, and then we're going to look at the rectangles. I'm going to pause the video and fill in some information, and then we'll come back to this. Okay, so I went ahead and filled in or drew the rectangles for the left rectangle approximation here, and did the calculation coming up to 87. Again, that's base is 1 for each of these rectangles, so I just took out a 1 and then added up all the heights, which is the same thing as base times height on these. And that gives us 87. Now let's think about the units of measurement on this for a minute. The base of the rectangle is measured in time, which is in seconds. And so we are multiplying this by the height of each rectangle, which is velocity, and that is measured in inches per second. Now, if we multiply base times height on each of these rectangles, the seconds will cancel out, which leaves us with inches. That means the area of each rectangle is a measurement given in inches. So this calculation for area is actually a unit of measurement of inches, not a square unit. You know, in geometry, when you did area formulas, your answers always came out to square inches, square feet, square meters, square whatever. But in calculus now, we're going to be using all kinds of different measurements, and so the area is determined by your units for your x-axis and your units for the y-axis when you multiply those units together. So the area represents the distance that the train traveled in this case. Now notice also that on this LRAM, the left height of the rectangle, the first rectangle, was determined by this first value here. And the last rectangle here was not determined by the height here. It was determined by the height of the previous number. Therefore, this 0, which is this y value, was not included in this calculation. So we went from 0 through 6 for the heights for a left approximation. Now for a right approximation, instead of going from 0 through 6, the first rectangle is going to have an area or a height that is determined by a y value of 12. And so the heights are going to go from 12 through 0. It's going to leave off the first one, because when we do our heights across here, we're doing from the right side across, which will be here, 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 and so on, and then connecting to make or complete out the rectangles. Now the area on this one came out to 87 also, or 87 inches also, but that was simply because we left off the first 0 in this case, but included the last 0. And the first one, we left off the last 0, but included the first 0. So it was the same value that we were leaving off in both situations. All right, so the last one we're going to get trapezoids. And so let's go ahead and connect the tops of these. Now we're going to connect this top to the top of this side right here. And so that's all we're doing, is just connecting the tops, which creates all these trapezoids here. Now keep in mind what we're doing is calculating some areas, and the area of this first region here, even though it doesn't look like a trapezoid, we're really using the same formula, because if you think about a trapezoid being base 1 plus base 2 times the height divided by 2. Look at this first base. The first base would be this side, the second base would be this side. This side has a height or value of 0. And so base 1 is 0, base 2 is 12. And so if you think about your formula, if base 1 is 0, what that really leaves you with is base 2 times the height divided by 2. Well, that's just the area formula for a triangle, which is what this shape is. All right, so I'm going to go ahead and pause the video and give you the actual calculation here on this. All right, so this is the approximation that we get using the trapezoids. And once again, this measurement is still going to be in inches.